So welcome back. It's time for our first invited presentation by Brett Downing. He'll be talking about Micro ROS and advanced robotics. I'm really looking forward to this talk. Brett's a really interesting fellow, very talented. I first met him about 10 years ago at the just prior to LCA 2012 with his sister Jenna and Daniel. They come over from Perth, and these mysterious strangers help us set up, tidy up, and they're going, who are these people? And yeah, and since then, if you ever need a sonic screwdriver, Brett will have one on him. So I think these days he carries around a pine saw soldering iron. So yeah, without any more to do, over to you, Brett. Take it away.
Great.
And also, I believe Brett will take some questions. Yeah, I'll line them up on the message system, please. Over to you. Thanks, Brett.
Great. I'd like to begin today by acknowledging the traditional owners of the lands we meet on today, and I'd like to pay my respects to elders past and present. I've come here today to talk about advanced robotics on microcontrollers particularly. A bit of background. ROS, the robot operating system, is a software framework that provides publish and subscribe messaging and packaging tools. It was started in about 2007 as a response to prolific abandonware in academic robotics departments. Every new student would build a new robot with new ways of talking to new components, and the rest would get scrapped year after year. And you were lucky if you ever got a whole robot, even a simple one, even for a moment. ROS offered messaging and software packaging conventions that were extremely strict and prescriptive, but fairly versatile. The defining feature of ROS was that it encouraged modularity, consideration for system integrators, and it allowed researchers to share basic functionality and package the research for others to fork and cite. ROS is based on a data flow framework. Most nodes don't have flow control like if or switch case. Nodes just receive messages and emit messages. So in a simple remote control example, you might have a joystick node which deals with the hardware of a joystick. It might emit a message with a strong typing that describes a joystick state. That might get interpreted by a teleoperation node, which handles loss of input and converts it into a motion vector in a coordinate space. This doesn't care about the shape of the robot, but it handles dead man switches and stuff. Another motion might subscribe to the motion vector and describe how the robot should move, but it's yet another node that's responsible for actually figuring out how the joints should all behave. This separation of intent is what makes ROS so appealing. Every robot that moves can be driven by every motion planner, every remote control. If you can prove your path planner on a milk crate with drill motors zip tied to the bottom, you can expect it to work on a state-of-the-art humanoid machine. Likewise, if some research lab has proven a computer vision mapping and planning suite, you can reasonably expect it to command a hacked vacuum cleaner. Maybe you'll need to provide some image processing power on a second machine. These aren't hyperbolic statements either. The messaging convention is so strict and the packaging is so prescriptive that it's actually very difficult to leak information around the abstractions ROS provides. More often than not, I've found that ROS packages fresh off GitHub just work. When you want to deal with the real world, you first need to collect some data, think about what that means to you, and then do something about it. Sense and act need to happen in particular places and in particular ways. This is where software meets hardware. Hardware is hard and it throws up all sorts of constraints. For a practical application, you might need high-resolution timers, you might need to deal with esoteric industrial protocols, you might have low power requirements or heat tolerance issues. These are things you just can't get on a regular computer. The thinking part is pretty flexible though. It only requires some computing power. There's no exotic hardware involved. It doesn't need to happen anywhere in particular. Things worth really thinking about, like map generation, often don't need answers right away. Things that need answers right away, such as obstacle avoidance, often don't need much thought. So the separation of duty, ROS2 nodes don't need to be on the same machine. In the example here, there's only a couple of nodes that actually exist on the robot, and those are over here, and there's a robot that's not showing up on a node over here that's not showing up. The rest is all on my laptop. All of the inverse kinematics, all of the joystick handling, all of the everything else. The ROS2 nodes automatically discover each other over the local network. ROS2 transport layers are deeply configurable and do support encryption and authentication. The hard work is all done on the laptop, while the robot can focus on doing things and measuring things. This separation of duty is why I'm so excited about MicroROS. It takes it a step further than just having a big machine and a little machine. Going back to sense, think, act, there's an implicit step between act that goes back around to sense, which is where the world has a think about you and stuff moves about. The trouble is the world doesn't let you have your turn in peace, and stuff continues to move about while you're trying to have a think. I'm going to take a detour from robots to talk about time. Until about 2010, PCs came with parallel ports, and parallel ports could interrupt the CPU. In a CNC machine, you could measure the length of a cutting tool by lowering it onto a conductive pad and stopping when you complete an electrical circuit through it. It was very simple to write software that could use the parallel port to detect tool contact, stop all the motors within tens of microseconds. The parallel port became obsolete and was replaced by USB adapters. The communication round trip of USB pushed the latency out to about a millisecond. The port throughput was the same, so consumer experiences were good, but motor commands would get buffered in the adapter, so an instruction to stop would get delayed behind instructions to advance. The additional buffering made the difference between an accurate measurement and a broken tool. As computers got more powerful, we expected more from them, more threads, more things at once. Modern task schedulers are amazing things. Some of them allow you to schedule operations to happen by some deadline instead of indicating some relative priority. This allows things like real-time audio processing on Linux, mouse cursors that don't stutter. Deadline schedulers are useful for robotics, but they're not enough on their own. Very often you need better timing resolution, so you need something to happen not just before some deadline, but at a specific time. If you've ever tried to use addressable LEDs on an 80 tiny processor and then do something else as well, you know it doesn't work. To get really good timing guarantees on a CPU, you need an ability for the CPU to drop whatever it's doing and respond to an external event, a CPU interrupt. Unfortunately, CPUs take time to do anything, and things have a habit of happening all at once. The more interrupts you want the CPU to service, the more likely it is that your interrupts will collide with each other and one will get delayed or missed. The more strictly timed code you try to write, the less of your code will be on time. I mean on time in the strictest hardware sense here, running a specific CPU instruction on a specific instant. Bit-bashed protocols and physics experiments. The promise of time sharing of a CPU is incompatible with the promise of handling multiple unpredictable events on time every time. The solution doesn't exist to be written down in a software framework. The way out is you compromise. You relax some constraints, limit the resolution of your timing guarantees, and then only guarantee that code will run before a deadline. That compromise is what a real-time kernel offers, and it's plenty for a lot of things that I didn't come here to talk about. The other constraint you can relax is the assumption that we have fewer CPUs than things we want to do. More hardware, less sharing of resources. More CPUs servicing fewer interrupts each, simpler CPUs that have more deterministic timing, or even specialized devices that can implement desired behavior without CPU intervention. A lot of embedded systems engineering for battery-powered devices boils down to corralling microcontroller peripherals to do all of the things while the CPU takes a nap. But less sharing of more hardware is not a solution, it's just a different problem. Fortunately, the throw hardware at it problem space is a little more tractable these days. If I have to leave the comfort of GCC on Linux and write my time-sensitive stuff on a microcontroller, I don't also want to write about passing messages back and forth between the micro and some host system, and then also write that on both sides of the communication channel. Using an Arduino for an out-of-chassis experience for a robot was so common that the ROS community made a couple of compelling attempts at getting ROS to work nicely with microcontrollers. ROS Serial provided a generic host-side node that could be instructed by an Arduino to interact with a host-side data stream. The Arduino side library let you set callbacks to be executed when messages arrived and pack messages to be sent. Overall, it was very clean, but it was a very clean implementation for ROS 1 by the time ROS 2 came about. It had a few issues though. Most Arduino boards have a physical serial port behind a USB converter, so they don't move data particularly quickly. ROS Serial also couldn't be extended to Wi-Fi or Ethernet when the ESP8266 became popular, or when Ethernet shields became cost-effective. Library support for the various messages had to be generated from host-side code and copied to an Arduino library. It was automated, but still a little rough on beginners. Because the serial port on almost all Arduinos and clones used USB serial emulation, they inherited a 10-meter limit to their tether to a host PC. It was common to see wireless bridges, OpenWRT routers, or XB radios, but they often doubled the cost of the actual robot. These limitations needed a systematic fix. Instead of wrapping some key functions on microside code and then leaning on the host for actual work, MicroROS builds ROS 2 natively for the target microcontroller. MicroROS provides a full-blown native ROS 2 interface for Arduino ESP and STM32. Because ROS uses mainline ROS 2 source, the developers were able to get incredible automated test coverage, which made for a really pleasant pull request experience on GitHub. Peer discovery is important for flexibility. By forcing a decade's worth of robot developers into a strict and modular design pattern, any host-side nodes ever written can talk to any microcontroller on the network without modification. MicroROS integrates with FreeRTOS, so you can have fancy threading stuff, or you can just write event handlers. I mean, you can take it as shallow or deep as you please. A lot of ROS developers these days are having to square with automotive safety integrity coding guidelines, so there's actually very little memory thrashing at runtime in MicroROS. MicroROS inherits the pluggable transport layers of ROS 2, which became way more significant than I expected. When I proposed this talk, none of the regular ROS transports would build on a microcontroller, so MicroROS relied on a host-side node to broker transactions through a simpler communication protocol. The MicroROS agent supported serial, UDP, CAN bus, but the agent sat on a host like the end of a tether, lending it a similar topology to ROS Serial. That tether could be Wi-Fi, but the agent was still a central point of failure on an otherwise distributed system. These simpler protocols were implemented as proper ROS transport layers, though. They just lacked the killer features that made ROS 2 so powerful. And then someone announced embedded RTPS. I don't have a slide for this one. ROS 2 ships with a default transport layers based on DDS, the data distribution system. ROS 2 treats it like a big old namespace that holds the current states of a bunch of values and updates them on any machine that cares. Behind the curtain, DDS is a lot more than that. DDS is provided for ROS 2 by a couple of vendors, and they're all notionally intercompatible for at least the basic features. One such basic feature is RTPS, real-time publish-subscribe. which handles most of the network transport tasks. RTPS is not to be confused with any of RTP, RTSP, RTMP, RTMPS, real-time publish subscribe, yeah, acronyms, and a cluttered namespace. Embedded RTPS had its first commits in 2018 and built an implementation of RTPS that works on microcontrollers with LWIP, the lightweight internet protocol, and Fri ROS, allowing it to target the threading and networking capabilities of STM32, Arduino, and ESP. Embedded RTPS announced on the ROS Discord that it had passed some compatibility tests with FastDDS, the host-side DDS implementation for ROS Foxy, in January 21. Then in October, the MicroROS maintainers had included it as a transport option in MicroROS, eliminating the need for the agent, bringing MicroROS into a decentralized topology with the rest of ROS. I think I'm going to go into demo time now. So I'm going to hope this all works. So these are all the nodes that I currently have running. And let's see. If I visualize what the kinematics is doing, that's actually up behind me. That's this one, with the camera pointed at it from a second robot. And then on the joystick, I can move all of the parts like so. So I've got a joystick input with a deadman switch, which is all handled on the host side computer. I reused all of these nodes for any robot that drives around. I've got an OpenSCAD model that has all of the inverse kinematics. All of the inverse kinematics runs on the host side machine, and then it sends the updated states to the microcontroller. So that's about all I've got. The microcontroller in this demo is the ESP32, and it's just running, it's accepting servo messages for, an array of, where am I? I can interrogate the topics that I'm using, and I can read off the commands that are being sent to, if I can type it, read off the commands that are being sent to the claw. So these are just, this is just an array of signed integers. Each one represents the angle of a servo motor. The joystick, again, is a standard message. With stick inputs. Stick inputs as floating point numbers, buttons as, I think, also floating point numbers. And this kind of standardization means that any developers can sort of share basic functionality of all of their robots. So the same messages I use here, I use on the other robot behind me, they all use very similar hardware. So the timing performance as demo is not great. I've kind of used the simplest implementation of sending just the updated state instead of sending like a schedule of motions to follow. So normally the reason you would want to use ROS on hardware is because you want strict timing. You want to have a motion plan come in from a host system. You can have motion commands come in from a host system with a sort of default e-stop behavior if something happens instantly on the microcontroller. If the microcontroller needs to respond to an event quickly, you can do that on the microcontroller. We've got a question about inverse kinematics. Where are we? Inverse kinematics. Sure. Kinematics is describing how a joint should move in order to achieve a certain result. So in the case of this claw, I've got the contact points where the claw should be moving around a circle. Kinematics is essentially where that contact point ends up for a given motor motion. Inverse kinematics is figuring out how the motors should move to achieve that desired motion. So here I have a gate synthesizer which describes a path plan. It describes a path through space, and the inverse kinematics engine tries to find joint poses that achieve those positions. And I did actually implement inverse kinematics on OpenSCAD. I kind of got a bit carried away. OpenSCAD being having its variables OpenSCAD's a bit weird. It's the simplest possible CAD language that you could use. So it's the simplest language that could solve a problem. Which means that it doesn't have like for loops or mutable variables or stuff like that. It just has like tail recursion. If you want to loop, you have to use tail recursion. So in this case, I have the animation loop figures out places for the contact points to be. And then it uses tail recursion to optimize the poses of all the motors to achieve those joint positions, and that all happens within OpenSCAD. That was really useful for figuring out, like, do these components all collide with each other? Have I made joints long enough to reach the positions they want to get to? That was also very good because I could export the model into ROS, but I could also export the kinematics chain. So I've just got a bunch of lengths of all the joints, all of the hinges and stuff. And I could just export those directly into the ROS simulation to generate this model. The connection between the computer and the robot is, you can take your pick. So at the moment, I'm using the MicroROS agent over wireless. So I've just got UDP transport over Wi-Fi. That thing is just battery powered off a drill motor, off a drill battery. And you can use a serial CAN bus. I mean, you can make any transport over anything as long as you implement it as an actual ROS transport. What sort of limits are there in MicroROS for hardware support? I'm assuming you can't do more complicated stuff that you would do on a full Linux host, e.g. connecting to LiDARs. Funny you mentioned that. LiDARs produce a fairly huge amount of data, and a lot of the time they just put it straight onto an Ethernet cable. So most of the time for a LiDAR, you've got LiDAR data coming from the unit over Ethernet into the host system, and then you've got a driver on the host system. But for vacuum cleaners, they have a little spinny LiDAR that just does a 2D scan. Those end up producing a fairly small, like a fairly modest amount of data. So those ones you can just attach to a microcontroller and then spool all of the ranges and angles out to a host system, or deal with them on the local device. So, like I mentioned, for map generation versus obstacle avoidance, if you have a 2D LiDAR, you can set up little zones where if you detect a hit within a zone, you know you've got an obstacle that you need to avoid. So you can have a function on the microcontroller that avoids the obstacle, like in a hardware real-time loop, and then you've got the host system picking up all of those points, intercepting all that data, and generating a map, and then building a motion plan for the robot to follow. So that way you've got all of the hardware real-time safety guarantees of an onboard hardware-backed obstacle avoidance system with the niceties of a more complex map generation and path planning tool. So a lot of the communications for MicroROS are not encrypted. I'm not sure that embedded RTPS has an encryption profile. So generally, ROS is all about researching quickly. So it's more about rapid iteration than safe networking practices. So DDS has automatic discovery on the local network. You can encrypt it, and SROS, Secure ROS, basically provides an API to manipulate the DDS security layers. All DDS vendors implement a security profile. It's just a mandatory aspect of like the minimum DDS spec. So you can configure that, but you end up locking nodes into, they stay in their one lane. They don't read or write to messages, topics they're not allowed to, stuff like that, which gets kind of in the way of, gets a little bit in the way of like iterating rapidly on new topologies for control systems. Oops. How much time do we have? I think we're about wrapping up.
Hey, I've just jumped back in again. Thank you very much, Brett. That was fascinating. I've got a couple of comments about what you just had on the screen a moment ago. One of the questions I don't think you followed up was, what is the inspiration for this design?
Oh,
when I first saw
yes.
it, I thought it was something like a hexapod on its back, but
right,
it's not.
So this is a reference to an art kinematic sculpture by Mark Setricane. I actually saw it first on Adam Savage's Test It. And when I looked at what they were using to implement it, I looked up the motors they were using, and it was like $500 a motor for 15 motors. And
15 motors.
15 motors.
So 5 arms, 3 motors per arm.
Yeah. So my pockets aren't nearly that deep, but I wanted to dabble with the, for Mark Cetricane, it was a skills sharpening exercise. So I wanted to kind of pay homage to it and sharpen my own skills by essentially replicating it.
That looks amazing. So in the animation, you have the sphere sitting on the 5 fingers. Have you done that physically?
I have. Unfortunately, these servos. So the reason the original artist used the fancy motors was because he can tune the control loop of the motor at runtime, whereas these are just $3 hobby servos. So I can't modify the control loop within the servo because it's an ASIC. It's just raw silicon.
Yes.
I find these are a bit squishy. So if you move them from their target position, they just apply some torque to get back, but it feels a bit springy. So I had this thing rotating a salad bowl. It rotated, but it was noisy and rattly, and the contact points weren't actually where I wanted them to be.
Yeah. Okay. Well, it's an amazing demo anyway. I love the visualization where you have the 3D representation and the physical object, and they're almost synchronized. It's very impressive. Yeah. I'm just having a quick check. A final question, I think, and we're just about out of time. It's almost lunch. Is do you have any examples of Micro ROS running in production or commercial systems?
So there are. The MicroROS team have a regular meetup online where they present to each other, and there's a robot chassis that they're aiming for, like urban cargo delivery, and they use MicroROS to handle communication between ROS on the host box and MicroROS on the motor controller. So instead of having some weird driver that you have to import dependencies for, you can push all of the dependencies out to the motor controller and have the motor controller interact with the native ROS system on the host machine. So that allows them to iterate very quickly on the nature of motion control on their platform.
Okay, interesting. So it allows a little bit more modularity or separation of concerns.
Yeah.
Okay, great. Well, thank you very much, Brett.
Thank you.
I've experimented a little bit with ROS in the past and found it a little bit impenetrable, but this is inspiring. It makes me want to look into it more. So yeah, thank you very much.
It's been a lot of fun.
That's great. And for everybody else, we are now going into the lunch break. We'll be back at about 1:20, and where I will be doing a talk about some problems, and I'm going to be trying to do some stuff live on the bench, and hopefully it will go wrong because that's when it's entertaining. So thanks everybody, and we'll see you soon.